Good morning, friends. I feel immense pleasure to be here again for my favorite course, Engineering Thermodynamics. This course is very useful for mechanical, aeronautical, chemical engineering student. Here we are talking about the power cycle. We have already covered the Otto cycle, diesel cycle and the dual cycle. We have also covered the numericals of Otto cycle, few diesel cycle, also the dual cycle also. We have just now covered the dual cycle problem, one numerical. However, we should further go for the problem solving for the diesel cycle, and we know that what is the diesel cycle. And so in today's lecture, I am going to solve two problems. That is the numerical problem 1, finding heat addition, heat rejection and efficiency of the diesel cycle. Numerical problem 2, finding heat addition, heat rejection and efficiency of a diesel cycle, another problem. So here, if you see, we are only concerned with the heat addition, how much heat is added, and from where we are adding the heat? We are spraying the fuel. By spraying the fuel, we are able to add the heat. But all the heat is not used for work production. Some heat is rejected. And this is very much compulsory. By the second law of thermodynamics, if you are not rejecting the heat, your process is not possible. So heat addition will be there and heat rejection is there. And if heat rejection is there, there will not be 100% efficiency. There will be always efficiency less than 100%. So that efficiency, and that is also explained by the second law of thermodynamics. So we are going to discuss here this all the process, and we know that by the first law of thermodynamics that del Q is equal to del W, means the heat addition minus heat rejection is equal to work done. So we can find out the work done also, and if you know the work done divided by heat addition, you can get the efficiency. So here Q addition, Q rejection, Q addition minus Q rejection is equal to net work. Efficiency is equal to net work divided by Q addition, and this will be always less than 100%. That is why the second law of thermodynamics says that you cannot get 100% efficiency. So as a researcher, we should try to optimize, we should try to maximize, but we should not think to make 100%. Otherwise, it will be waste of the time. Now, I will go for my first problem on the diesel cycle. So here an engine works on diesel cycle with initial temperature and the pressure 17 degrees centigrade and 1 bar respectively. Pressure at the end of the compression stroke is 35 bar. An engine works on diesel cycle with initial temperature and the pressure 17 degrees centigrade and 1 bar. So initial P1 is equal to 1 bar. T1 is equal to 17 degrees centigrade plus 273. So this is the 293 Kelvin. Pressure at the end of the compression stroke is 35. So P2 is equal to 35 and this is equal to P3, because if you see here PV diagram of a diesel cycle, 1, 2, 3 and 4. So P2 is equal to P3. So at the end of the compression stroke is given P2 is equal to 35 bar and this is also equal to P3. And the compression ratio is 5. So P2 This is the V1, this is the V2. So P2 by P1 is equal to V1 by V2. It is given. This is given as a 5. So find the heat addition. So we have to find out QA, means from 2 to 3 how much heat is added. This is the QA, and here is the QR, and how much heat is rejected, and the efficiency eta we have to find out. QA, QR and eta, these things we have to find out. So we will go ahead and we will see that how we can solve the problem. So here I have drawn the PV diagram. In this PV diagram, 1 to 2 is a isentropic compression. I will draw here the TS diagram also. So 1 and 2 is isentropic. So 1 and 2. This is a isentropic compression. 2 to 3 is constant pressure heat addition. So I am just drawing here P is equal to constant, and here a small curve has come here. This is the 3 at P is equal to constant. Now 3 to 4 is a isentropic expansion. So in this is the 3 and 4, and from here the heat. So if I see here, from here to here, this is the getting cooler in this direction. Here also if you see, it is very hot here. Slowly it is getting cool here. So I will make some less color. Here it is hot, pressure and temperature. It is temperature is T2. This is the T1. This is the T3, and this is the T4. If you see here, P2 is equal to P3. This is the P1 and this is the P4. Here if you see, this is the V2, this is the V3 and this is the V1. So here I have shown the pressure, volume and the temperature. This is the TS diagram and this is the PV diagram. So here we can visualize that how the pressure and the temperatures are increasing or the decreasing, that we have to see before we start any problem. Hope this PV and TS diagrams are very much clear. So now it is P1 is equal to 1 bar is equal to 100 kilopascal. T1 is equal to 17 degrees centigrade plus 273. Always we have to use the Kelvin, not the degree centigrade, because absolute temperature is so. For this centigrade, we have to convert to the Kelvin. And also P2 is equal to P3. Both are the same. So pressure is given 35 bar. So 3500 kilopascal. The compression ratio is given as a 5. So process 1 and 2, to find the heat addition, we need T2 and the T3. And for the rejection, we need the T4 and the T1. So how we can get these all things? So we will first take the process 1 and 2. So T2 by T1 is equal to P2 by P1. And P2 by P1 is, P2 is given 35, P1 is given 1 bar. So P2 by P1, gamma minus 1 by gamma. Gamma, the value is 1.4. So T2 is equal to T1, 35 by 1. 1.4 minus 1 divided by 1.4. So here T1 is here 290. So 290 into 35 to the power 0.4 by 1.4, and you will get the T2 is equal to 108 Kelvin. So I am writing here 108 Kelvin. In this TS diagram only we can write. clearly. So now this is the P2 is equal to 35 bar. So now we got the T2. So now we have to find out the T4 and P4. This point we have to find out how much is T4 and V4, because we got this, we got P4 and P3 and T3. Now the last point is P4 and T4. So we know that process 3 and 4. So P4 by P3 is equal to 1 by RC to the power gamma. So here is P4 is equal to P3 divided by RC to the power gamma. This is the compression ratio is given. So compression ratio is 5. So P4 is equal to 35 divided by 5 to the power 1.4. So we will get P4 is equal to 3.67 bar. So here you got 3.67 bar. So we got this P4. So now we have to find out the T4 also. So we know that the process to find the T4 at a constant volume presses. So we know that T4 by T1 is equal to P4 by P1. So T4 is equal to T1 P4 by P1. So P4 by P1, T1 is 290 and P4 by P1 is equal to 3.67 by 1. So we will get T4 is equal to 1066.37 Kelvin. From here we can also get the T3. So V3 by V2 is equal to T3 by T2, and this is called the gamma. This is called the rho is equal to RC by RE, and so T3 by T4 is equal to RE gamma minus 1. So this T3 is equal to T4 RE 1.4 minus 1. So T4 we got, and we know RE is equal to 5. So it is 0.4. So T3 we got 2030. So if we draw here, this is the 1 to 2, 2 to 3, 3 to 4, T1, T2, T1, this is a TS diagram. T1 is equal to 293, T3 is the 2030 Kelvin. This is the highest temperature. Then T4 1066.3 Kelvin. And if you see the T2 we got 801. So actually this is not correct. Just I will try it again. It is not correct one. I will just again rub it, and I will draw the correct PV diagram as per the result which we have got. So 1 and 2, 2 to 3, 3 to 4 and 4 to 5. Like this it will come. 1, 2, 3 and 4. So one temperature we got T1 is equal to 293 Kelvin. T2 is equal to 100.101. T2 is 801. T3 is equal to here 2030 Kelvin, and T4 is equal to 1066.37 Kelvin. So these parameters we have got. We have also got the P4, T4, P4, P3 is already okay given. So this we can make it in the PV diagram also the same way which we have. So it is a TS diagram of the results. So whatever result we have got, we should be able to analyze that how much we are getting. So if you see here, T3 is the maximum, it is 203, but T4 is also not less, it is 1066. If it is coming to less, that much efficiency we will get. So as a researcher, as a designer, we should make sure that the 4 points should be below. As much you can make the below, that much this line is effectively used for generation of the work. Generation of the work. And as much you have the more work, that much you will get the efficiency. That we have to ensure. And this is the QA and this is the QR. So as much it is lower, that much heat rejection will be less. So that we have to see it, and that much we will try to find out. So here we can now find out the Q in means how much heat is added. It is equal to Cp T3 minus T4. So here T3 is this one and T4 is this one, 1066. So heat in is equal to T3 minus T2. So T3 is 2030 and T2 is equal to 801. So here 1.005 2030 minus 801. So 1234 kilojoule per Kelvin. That is the one answer. They ask how much heat is added and how much heat is rejected. Q out is equal to CV T4 minus T1. So CV is equal to 0.717. Why we are taking the CV? Because this process 4.1 is at a constant volume. This is in a constant volume process. This heat rejection. So we use the CV, not the CP. And heat added is at the constant pressure process. So this is a constant pressure, and at rejection it is a constant volume. So we use the specific heat at constant volume, and here for heat rejection we use specific heat at constant pressure. And we should remember that for air it is 1.005 Cp, and for the air the CV is 0.717 kilojoule per Kelvin. Okay, that we have to understand. So here 1066.37 minus 290. So here we will get 557 kilojoule per Kelvin, and here 1234 kilojoule per Kelvin. Now to find out the efficiency of the diesel cycle, we know that 1 minus Q out by Q in. So 1 minus 557 divided by 1234, and we will get 0.55, and this if you multiply by 100 in percentage, this diesel cycle is equal to 55%. So this is the answer for this problem, and this indicates that so we can come to know here that 45% of the energy is waste, that is rejected from the rejection source. So here Q out, how much we can reduce this number, that much better efficiency we can get. But lot of research work is going on to reduce this and increase this. So how we can increase and how we can decrease, that we have to think. Okay, we all should try to think in this line, that what are the process by which we can decrease this, and what are the process we can increase the Q in. So that we can discuss in some other classes. So I am going for my next numerical after this. So an engine works on a diesel cycle with initial temperature and the pressure 290 Kelvin and 95 kilopascal respectively. The compression ratio is 20. It is not ration, it is ratio. Compression ratio is 20. Volume at the starting of the compression is 0.5 liter. This is the volume is given, and the maximum temperature is 1800 degree Kelvin. Find heat addition. So what we have to find? QA, QR and eta of diesel. So this we have to find out, but here some parameters are not the same as in our previous cases. So little changes, little concept we have to change. method is same. We have to find out the QA, we have to find out the QR, then we have to find out the work done, we have to find out the efficiency of the system. So here we will go for the solution, and this here we have the R is given 20, and this P1 here, this is the P1 95 kPa, T1 is equal to 290 Kelvin, and this T3 is given as 1800 Kelvin. V1 is equal to 0.5 liter. Okay, so these parameters are given to us. So we have to start with process, and it is engine. So we have to put the arrowhead in the clockwise direction. 1 to 2 here is a isentropic compression. 2 to 3 is constant pressure, heat addition. This is the isentropic expansion, and this is the V is equal to constant, and this is the heat rejection. Okay, so here I am putting QA and here QR. QR is moving out. So for the process, it is 1 to 2. It is isentropic process, isentropic compression. So we know that P1 V1 to the power gamma is equal to P2 V to the power gamma. So this P2 is equal to, here P2 is equal to P1 V1 to the power V1 by V2 to the power gamma, and this V1 by V2 is given 20, and this is 95. This is the 95. So we can write here that P1 is equal to 95, 20 to the power 1.4. So we will get here 6297.5 kilopascal. So this we got P2, but P2 is equal to P3 because it is a constant pressure process. So P2 and P3 are same. So both will be 6297.5 kilopascal. So we got the P2 and P3. So to find the net work done, what we have to do? QH and QL are required, and we know that QH is equal to CP T3 minus T2. So CP is 1.005 and T3 is equal to 1800 minus T2. So we have to find out what is the T2. So how to find out? We will see that T1 V1 to the power gamma minus 1 is equal to T2 V to the power gamma minus 1. So T2 is equal to T1 V1 by V2 to the power gamma minus 1. So 290 into 20 to the power 1.4 minus 1. So we will get here this value, that this value we got it here 20. So if you put this value here, then you will get the QH. Please find out. Please calculate. I am giving you as a homework so that you will also do something. Please calculate. Now we have to find out the QL. How much is the heat rejected? It is a CV T4 minus T1. So this we will see here. So how? So you can get the T4, T1 we know, and if you put this value, you have to find out all this thing. So heat rejected QH is equal to 1.005 1800 minus 290 into 20 to the power 0.4, and QL is equal to 0.717 into minus 290 Kelvin, and here T4 we can find out by the help of your constant volume process by this V1 and V2. So in this way we can do it and try to calculate this thing, and neta we can get that QH minus QL divided by QH. So these all things can be calculated by the help of this process. So these are the references which I have taken, that is PK Nog, Engineering Thermodynamics, Tata McGraw Hills, 4th edition. Eunice Senegal, Michael A. Bowles, Thermodynamics and Engineering Approach. Then NPTEL lecture from Dr. Mishra, IIT Kanpur, that is Aeronautics and Astronautics, Engineering Thermodynamics. Any questions you are welcome to ask, and you can also write the comment. Please like and subscribe this channel. Thank you very much. Be tuned for the next lecture. Till then, goodbye. See you.
Like, share and subscribe. Hit the bell icon for more updates.